Hey everybody, it's Kyle from Kyle Tuned It. I'm here today to share with you a tutorial on the methods used to set up custom safety features using DS1's custom maps. This is going to give us standalone-like safety monitoring to make sure we don't blow our engine when we start to push the limits. Before we get started, click the subscribe button to our YouTube channel, check out our website, and make sure to follow us on Instagram and Facebook so you can keep up to date with our latest and greatest. Also, leave me a comment below. Let me know what you think about this video and what other tutorials you'd like to see next. Okay, so let's take a look at what we're trying to accomplish here. In the left side, I have the custom map folder structure. We have the LPFP knock safety currently open. That used to be called custom map 10, and now I've renamed the folder to LPFP knock safety by using the XDF header editor, which is on the bottom right. You can get there by pressing Control F2 in Tuner Pro and scrolling down to the 200s. That's where the custom maps are in the Dyno Spectrum XDFs, and you can rename them there. Then inside that folder, I have renamed the unsigned XYZ map to LPFP knock safety, and I've deleted the rest so that we don't get confused with anything. We only need to keep the one that we're using. You can also see on the top of this screen, I've taken the monitors.csv file, renamed the custom result maps for the ones that we are making custom maps for so that I can monitor what they are doing in the data log from now on. And then also I have the highlighted blue ones, which are the RAM variables that we're going to be using in order to make the custom maps. Getting all this stuff ready is going to make it a breeze to throw these custom maps together. So the next part might be the hardest part of this entire tutorial. We have to work directly with the hexadecimal bytes that is going to go into the caller map in order to activate the custom maps. So I'm going to use the Windows calculator, switch it to the programmer mode, select the hex option, and then I'm going to go over to the second tab over, which is an actual representation of the individual bits. So if you can see on this left one right here, we're going to start counting, and the bits are numbered, and they go from right to left. So the rightmost bit is bit 0, and then 1, 2, 3, and then we have 4, 5, 6, 7, 8, 9, 10, 11. You'll notice on that first one on the left, I have the 10 and the 11 switched to a 1, and that is going to make our hex reading on the top show us C00. So that binary representation of those bits is going to give us C00 as the hex code. The bit position corresponds to the custom map number. So the 0th bit is custom map 0, the 4th bit is custom map 4, and so on, all the way up to 15. 0 through 15, there's 16 custom maps total. So I have C00, that's going to activate custom maps 10 and 11. So I'm going to put that over in the caller map, and I'm going to call those custom maps once every 100 milliseconds. That is going to be for custom map 10 and 11, which are the low pressure fuel pump safety, the knock safety, and also the short-term fuel trim safety. The next one I'm going to do in this middle view right here of the calculator, which is hex code 1000, 1000, and that one is only going to activate custom map 12, which is going to be our Lambda safety map. Now that one, just due to Lambda spikes and how it settles in when we're in boost, we're going to make that one call once every 1000 milliseconds, or once per second. So then I go and put 1000 into the 1000 millisecond task in the caller option, and then that will activate how it calls the custom maps. Okay, here we're going to continue with the custom map settings for our first custom map, which is for low pressure fuel pump and knock safety. I'm going to go through these kind of fast, so if we need to get some clarification on any of these steps, simply leave me a comment and I'll go ahead and respond back with a little bit more clarification. First of all, we have the mask of maps, which is enabled. I only want this custom map to be enabled on maps 1 through 9. I'm going to skip map 0, since map 0 is going to be our safety map and the one that it's going to switch to when there's a problem. So map 0 would have a lower boost, or load target in order to save the engine if something goes wrong. We have the calculation is 0. We're just going to look up the value off the table. The action is 100 to switch the map. Next, we have the variable types for X, Y, and Z. The X is an unsigned 8-bit, Y is an unsigned 16-bit, and Z, which is the map switch, is an unsigned 8-bit as well. We have the X and Y address for our variables that we're looking up. And then we also have the enable address for relative load, because I only want this to be enabled when the relative load is above 150. Then we get over to the enable type, because relative load is also a 2-byte variable, unsigned 16-bit. And then we have our enable minimum and maximum. Those are the raw values which can be calculated from the scalar information in the monitor's file. Okay, on this next slide, I have our axis information for the x-axis. So this axis is the knock average. On the first screen, the general tab, I'm going to change the decimal places to 2 and the cell data size to 1 byte. On the conversion tab, I'm going to pull the conversion information straight out of the monitors.csv file. I can see that on knock average, the raw value gets multiplied by negative 0.75 in order to tell us the actual degrees of knock. So that's what I want to show up on the table so that I can edit it in units that I understand. So I put that in the conversion and then I click OK to save that. Then you'll notice on the bottom, I can now set up my axis and I can have them, since the raw value each time it increments by 1, it's going to go up negative 0.75 actual units. That's what I'm going to see on the axis. I can't actually put a value in between those because the raw value doesn't allow that. You can't have a partial number when it's stored in a byte. So that's what the conversion does, is it multiplies the raw value to an actual readable unit. And that's just how they have it stored in here for this variable. Each variable is going to be different. You can see over on the right side, I have it viewed in raw hex. You can see how it goes from hex value of 00 to 01, 02, 03. And that corresponds to the actual values of negative 0.75, negative 1.5, negative 2.25, and so on. Another important thing about all of these custom maps is that if I want to get a very quick map switch, I have to make sure that the switching raw hex value increments by 1. That way when it crosses that value, that's when it'll trigger the map switch. If I have too much space in between the raw value, then it'll take some time to bring the map switch down. It will actually be interpolated and it won't happen until the value is actually at the next value. So that's one thing to be careful of while setting this up. The next one here, we have the y-axis. Same story. I'm going to pull the conversion out of the monitors.csv for the low pressure fuel pump pressure, which is x times 0.1. That's the raw value times 0.1 in order to give us the kPa pressure value from the fuel pump. This one's a 2-byte variable, and I only need to see 1 decimal place because it can't ever have more than 1 decimal place according to the math function. Now we get to where this is all coming together. And I have on this screen, I have the y-axis on the left side, the x-axis up top, and I have the custom map already populated. So let's just go through this and see how this works. On the x-axis, I have all the knock values, and they're incremented in raw values of 1, and it shows the actual value of the knock degrees on the x-axis. Then I have on the y-axis the actual fuel pump pressure. Now, once again, you'll remember I said it needed to increase by 1 raw value, and we know the raw value was x times 0.1, which means each raw value is going to go up by 0.1. So in this case, it would be 499.9 kPa up to 500 kPa. I can make all of the values that we don't care about the same as long as it's in an increasing manner. So basically, this entire table in the y dimension will only flick between the top 2 cells. It's going to look up the bottom ones always the same, and it's not going to matter, but they all have to have the same value. The same on the axis as in the table. So if I look on the main table now, I can see that I'm going to allow up to map 10 if I am at 500 kPa or higher. And I'm also going to allow map 10 if I am at 3 degrees of knock retard average or less. As soon as it goes over 3 degrees knock retard or goes below 500 kPa, I block it to 0 and it switches to map 0 to save the engine. Here we can see the raw values. So on the y-axis, for example, the raw value of 1387 corresponds to 499.9 and 1388 is 500.0. As long as this always triggers between two raw values, that'll ensure it map switches as soon as it drops below that one specific number. Without that, there's no way to guarantee until it passes fully down below the next number down. Okay, now we'll move on to custom map 11. This is going to be short-term fuel trim. What we're going to do is we're going to look at the closed loop that the ECU is doing to match the Lambda target. And if it goes too far positive, that means it was about to run lean and the ECU is trying to catch up adding fuel. We run out at 25%. So as soon as I get to 20%, I want to just cut things down and say, look, we've got a serious problem with the fuel. Let's just cut our losses and switch to safety map. And then you'll be able to see what happened in the data log later. This is very useful during tuning port fuel injection and methanol and different size injectors and stuff like that to make sure you don't hurt the engine. We'll go through the settings that are the same on this one as the previous custom map. So we have the mask of map switches enabled, the calculation, the action, the enable address, the enable type, the enable minimum and maximum are all the same as the other map. And they'll be the same for all of these custom maps. The ones we do need to change are the X, Y, and Z type. The Z type is going to be the map, so that doesn't change. The X and Y type are both unsigned 16-bit, so those are type 2. And then we also need to put in the X and Y addresses for those respective variables. In this case, it is Lambda fast control bank 1 and bank 2. Now here we have the X and Y axis conversion and settings. These ones, the raw values correspond to a very, very small number. So the conversion is X times 0.0000305, and I'm going to display 7 decimal places of this. That's not necessary. We only really care about the raw values, but I'm just going to show it so that we can see as many digits as possible so we can see what the values actually are. Okay, so now we can get to the brute force of how custom map 11, which is our short-term fuel trim safety, is going to work. We can see based on the x-axis and the y-axis, which are banks 1 and 2 short-term fuel trim, up to a value of 1.1999615, we're going to allow up to map 10. If it crosses over to above that first axis value on x or y, then we instantly dump to map 0. Once again, here's a raw hexadecimal view of what that looks like, and we can make sure that our values go up by an increment of 1, which makes it so that as soon as it goes up one step of 0.0000305 of raw value, it will trigger that map switch immediately instead of taking some time to hit that next value. Here we go again on custom map 12 now. This is going to be our Lambda safety map. So we have once again the same values. On the mask of map switches enabled, the calculation, the action, the Z type, enable address, enable type, enable minimum and maximum. Those are straight copied from the other maps. The ones we need to change for this map is the X and Y type. Once again, those are unsigned 16-bit, so type 2. And then the X and Y address. We're going to use the X and Y address for Lambda actual bank 1 and Lambda actual bank 2. And now we get to the axis definition for custom map 12. It's the same on the X and Y axis. We're going to pull out our conversion from the monitors.csv for Lambda actual bank 1 and bank 2, which is X times 0.000244141. That's how the raw value gets converted into an actual Lambda number. And then we're going to show 7 decimal places of that in the axes. And once again, here's a full look at how custom map 12 works. Same idea as the short-term fuel trim map. Under Lambda of 0.8750013, we are going to allow up to map 10. That's on the x-axis and the y-axis, which is bank 1 and bank 2 respectively. And as soon as that lambda value goes any higher than that on either bank, it instantly forces map 0. And here's a look at the raw hexadecimal values, just so we can make sure they increment by a value of 1. Use that Windows calculator if you have any doubt in your mind that it's going up by 1. You can use the hex math and simply take a number and add or subtract 1 to it in order to get that value. Last but not least, what we're going to do in the monitors.csv file, I have renamed the custom result 10, 11, and 12 so that I can recognize those in a log. So I put in the titles of each map on each respective result. And then we've also changed the scalar and the offset because the output of those maps is going to either be a 10 or a 0. We've assured that by making sure the axis values increment by 1. So it won't allow it to be any other value besides 10 and 0. So if I take those values and multiply them, as you can see here, I will get either a 0 when it's a 10, or I'll get a 1 when it moves down to 0. Just a little bit of clever math to make it so we can see when each custom map is activated. And then last but not least, we have the settings in map 0, which are going to force safety on us. We're going to allow a maximum of 150% relative load or 1.5 absolute pressure ratio. That's going to usually close the throttle and drop the boost all the way down if this happens and it triggers map 0. And now we can look at this data log and see the results of what we have set up. For example, in this case, the low pressure fuel dropped below 500 kPa, which is the threshold we had set. Instantly the boost drops, the throttle closes, and prevents any engine damage from happening. All right, you guys, we made it. I know that was a lot of information. Hope that helped understand a little bit about one of the cool things we can do with the Dyno Spectrum custom maps. Engine safety is a big help when we're really pushing the power, and we don't want to think about it. Let's just let it happen in the background, just like the most expensive standalones out there. You can do this on your factory ECU. Thank you guys for watching. Don't forget to click subscribe. Let me know what other videos you guys like to see, and we'll see you next time.